Okay. Fair enough. Or yesterday's, I mean.
Yeah, that's what I meant.
You're going to watch yesterday's video tomorrow.
You know what I meant.
I know what you meant. Okay. Okay, here's a question that I would have given you guys to solve last year. And I think last year, if you guys remember, it's been a while now, but like when we first started doing math, if I give you a question like this, you probably would have been like, holy smokes, this is intense. And maybe even you're having some flashbacks going like, holy smokes, what do I do? Okay. I want to actually just solve this one with the group, and then using this example, I want to make a point as to where we're going to go today. So, anyone have any thoughts as to how to go about solving a question like this? What could you do? Okay, so foil everything you can. So that'd be like this bit here you could foil. Yeah, you can't really foil this because there's not a full bracket there, but you can like do that if that's what you need. So why don't we start there then? So you'd have 3x and 5x squared and 9. This one I missed. 15x. Not necessarily in that order, but those would be the 4 terms. Does that work? And then over on this side here, we'd have to leave that -2 sitting there because it's not part of the FOIL. It's just off to the edge. And then the 4 would expand to give that. Does that work so far? You're allowed taking attendance. Okay, any thoughts as to what to do next? Sure. Combine like terms is maybe a phrase we'd use, right? So you could actually combine a couple terms over here too. Maybe you could call this 5x squared plus 18x plus 9. And then over here you could say you have 4x minus 6. Does that work? And one more thing, I'm going to try to do it together just to save a step. See this x plus 2 right here on the bottom? One of the ways that we learned last year to kind of deal with solving fractions, and I know we're working with fraction. Do you guys remember what we call it if it's a fraction, what like the official term for that is? It's called a rational. So something that's a fraction is rational. Anyways, this is a rational expression right here. One of the ways that we learned last year to fix this is to times the x plus 2 up to the other side. So it makes sense if I kind of threw that right over here. Kind of like swung that up there. Then let's FOIL again. So FOIL this guy, you'd have 4x squared. Actually, there's any more pluses. You'd have a minus 6x, but you'd have a plus 8x, and you'd have a minus 12. So putting this all together, you'd have 5x squared plus 18x plus 9. That's going to equal 4x squared plus 2x minus 12. So far, so good? Okay. You guys remember what we would do next? Sure, that'll work. What did you say? Sure, basically you both said the same thing in different ways. Subtract one side to the other, make it equal to 0. So you'd have x squared if you brought the 4x over. You'd have 16x if you brought the 2 over. And you'd have 21. And that would equal 0. This is a major thing we worked on last year then. Last year I needed to show you guys how do you solve something that looks like this. And last year's goal was all about quadratics and the quadratic formula. Does that make sense so far? Well, guess what this year's goal is then? Can we solve things that go to the power of 3, or 4, 5, or 6? Does that make sense? You guys have been learning how to solve equations for the last couple of years of math. Back in grade, whenever you first learned algebra, you guys were learning how to solve linear equations. Like, for example, when, I don't know, Mr. Bond or Miss Vadnais first introduced algebra to you, they probably said 3x plus 4 equals 9. Right? And so you learned how to solve something linear by subtracting 4, 3x equals 5, divide by 3, divide by 3. There, you have an answer. Does that make sense? We spent a huge chunk of time last year then focusing on, well, what happens if you have specifically x squareds? And I mean, the best way of solving was that quadratic formula that should basically always work. Does that make sense? The last 4 lessons, I've really given those all with the purpose of building up to today's lesson. Our goal today is, I'm going to skip ahead in the slides here a little bit, is to solve something like this. For example, if I made it 0 equals x to the third minus 3x squared minus x plus 3. That's our goal, try to solve that. Does that make sense? Here's the problem. You know how there's a quadratic formula for x squareds? There really is no cubic formula for x to the thirds, or quartic formula for x to the fourths. So we need to show you a different method. Okay? And so that's why the last 4 classes have been really important, in that I've been kind of trying to build background skills that we're going to need to get to this. I was joking with Brad earlier today that, you know how last day I kind of taught you guys a whole bunch of stuff for an hour, and then I showed you like the actual remainder theorem is like literally here, just plug a number in and it'll tell you the remainder. That's kind of what like the last 4 days were for. It was like, if I really wanted to, I probably could have just started with this lesson here, but you guys probably wouldn't have had the background skills needed. Does that make sense? So to me, this is kind of like the key important lesson of the whole unit, is how do we solve something that is not to the power of 1, or something to the power of 2, but something to the power of 3 or more. Fair enough? Okay, so let's show you how. Before I do that, just a couple of reminders of key words, because I want to use the right terminology here. A polynomial should be able to be written sometimes like this: x minus a, x minus b, x minus c. Sometimes I like to call this factored form. Makes sense? Where we try to write it as, like, say, y equals x plus 2, x plus 1. That's a factored form. Another way of writing it, though, would be y equals x squared plus 3x plus 2. Do you guys remember what it is when we write it kind of like this? What the name of that is? Good. Okay, yeah. So standard form is usually how something is going to be given to you, but it's not as useful as factored form, because if you have a factor of x plus 2, the root is minus 2. Does that make sense? If you have a factor of x plus 1, the root of that is minus 1. Does that make sense? So I just want to make sure we're all clear on the term factors and roots. Okay, here is why we did one of yesterday's things here. One of the ways to try to find a root is to use long division. If you can divide a binomial without getting a remainder, it must be a root. So that one more time. If you wanted to try to find a root of some sort of big, long thing here, what you could do is do long division. However, there's one little thing here. You have to not get a remainder. And that's pretty rare. Also, long division takes a long time. Even synthetic division takes a long time. So we want to use yesterday's skill of the remainder theorem instead to help us out. Because as good as long division is, it's inefficient. I think I've made this point. You guys are clear on the difference between roots and factors? This is the factor, but like R1 would be the actual root. Okay, let me walk you through how we might try to solve some of this thing here. What we could do, I'm only going to do this once, because this is so inefficient. But what I could do is randomly try to do long division, or synthetic division, and just hope to pull a random factor out of nowhere. Okay, so I'm just going to guess something that could logically be like a factor of this. You know? Maybe x plus 1 could be a factor. I mean, x plus 1 is often a factor. So what I might try to do is go x plus 1 and long divide it into this whole thing here. I'm actually going to use synthetic division, though, because I like that one better. So synthetic division means you put the coefficient of 1, minus 3, minus 1, and plus 3. So I'm just going to review synthetic. If x plus 1 is going to be a factor, what's the remainder need to be? Okay, so we're just going to throw mud at the wall and hope that it works. Drop down the 1. 1 times 1 gives you 1. That's that bounce idea. 3 minus 1 gives you minus 4. 1 times minus 4 gives you minus 4. Bounce that up here. 1 minus minus 4. 3. 1 minus minus 4. Yeah, you're adding 4. 3. And then 1 times 3 is 3. 3 minus 3 is 0. Blind luck. Because honestly, I just randomly, okay, I did fully randomly, but I just randomly picked x plus 1. But here's the question. How are you going to know whether you should pick x plus 1 or not? Does that make sense? You don't. I just randomly picked a number. What was that? How so?
Start with 0 on that one side, and then.
And like go back the other way?
Yeah.
I've never actually seen that done before. Let's play around with it later. I've never thought of that or heard of that before, but maybe. Does that make sense what I'm doing so far? Here's what this means then. I can break this guy, this equation up here. I'm just going to write this out. X to the 3 minus 3x squared. Oops, that's a screw up. X to the 3 minus 3x squared minus x plus 3. What it equals then is x plus 1 as the factor that I just found times by what the leftover stuff was. Do you guys remember how this bottom row here is supposed to be notated, like what it means? Not cubed squared. It'll work backward. Work from this side here. So this is the remainder of 0, which is what we're hoping for. This is the constant term. So that's your x, and that's your x squared. So it means that if you were to refoil all of this mess out, you should get that. Again, the x plus 1, I knew x plus 1 was going to work. That's why I went with it. But how do you know to start with x plus 1? Does that make sense? You could have tried x plus 2, or x plus 3, or x plus 4, or x minus 7. All right? And you're just kind of randomly throwing mud at the wall and hoping it sticks. Okay? So one more thing here. This thing right here is now a quadratic. How do you solve, how do you factor a quadratic? Do you guys remember? Yeah, plus minus, like you're looking for numbers that, I hope this is what you mean. Things that add to give minus 4, and things that times to give, perfect, negative 1, negative 3. So you have x plus 1, x minus 1, x minus 3. Ta-da, it's factored. So let's say we wanted to solve this thing now, or look for roots. Roots and solving kind of mean the same thing. If I have 3 binomials of x plus 1 and x minus 1 and x minus 3, then my 3 answers are minus 1, plus 1, plus 3. Does that make sense? So factoring and solving something to the power of 3, I've slowly been kind of working on skills to build up to this point here. There's one fundamental flaw. The linchpin to getting started was how the heck do I figure out what to put right here? Does that make sense? It's very frustrating because it's like, well, the first time I used x plus 1, but if I had used x plus 2, let me just walk through this real quick, just make my point really clear. If I did the exact same thing with, like, say, 1, negative 3, negative 1, 3, but I had done it with x plus 2 right here, yeah, like that. This would not have worked. You'd have dropped down the 1. 2 times 1 is 2. Subtracting those would give you 5. 2 times 5 would give you minus 10. Subtracting those would give you 9. And 2 times 9 would give you 18. Subtracting those would give you negative 15. And that's just not going to work. Does that make sense? Okay. So yesterday we talked about something called the remainder theorem. We're going to use the remainder theorem to help us figure out what number to use right here. Okay. So the remainder theorem said yesterday, if you want to try to figure out the the remainder, what you do is you plug in if you have a factor, you plug literally the root into the equation. Does that make sense? So like, for example, I could have done this whole synthetic thing a lot faster. I need even more room. What I could have done is I could have just plugged negative 1 to the third, 3 negative 1 squared. That would just be negative 1 there, and plus 3. Does that make sense? The theorem from yesterday, the factor theorem, or remainder theorem, basically says, if you want to test the x plus 1, plug the negative 1 into the equation, and if it equals 0, it's a root. Does that make sense? That's what we'd like to use. Okay. So today's concept then is the factor theorem. Honestly, it's very, very similar, but it's very wordy again. So let's see if I can put this into people words for you. Okay. The factor theorem then states that if x minus a is a factor, if you plug in the a, it equals 0. It kind of means the exact same thing. Let's see if I can make this better. Let's say it was x minus 1. if this is a factor, then if you plug in +1, it needs to equal 0. Does that make sense? If this thing actually is a binomial that you should be able to get, you know how you're supposed to hopefully get like 3 of them in a cubic? And if we're going to do a quartic, are we going to get 4? That makes sense. Etc. If this thing's going to be a factor, then plug in the +1, and if it makes it equal 0, then you found your answer. We're going to use that principle then to try to figure out which numbers to randomly guess when we do our long division or synthetic division. Because again, we still don't know what numbers to use here. Do you guys remember the 4 basic ways of factoring before I keep going further? Just quick review of factoring before I go any further. Here's a common factor. How would you factor this guy? Okay, and then if you pull out the 3 and the x, you're left with? Okay, so if this is a factor right here, what's its root? -2. What about this guy right here? Is that a factor? Yeah, actually 0 would work. Okay, why don't we try this one here? How do we solve one of these guys? Actually, we just did this one earlier, didn't we? This would be like x plus 2, x plus 1. Because you're looking for numbers that add to give 3 and times to give 2. So that means this one's -1 and this one's -2. Let me skip down to the last one. Do you guys remember how to do difference of squares? Okay, good. So Brad remembers here. I want to explain how to know when to do that or what you did. Go ahead.
The second number is like square rootable.
That's a word now. Yeah.
And then if it's like subtract.
Yeah, basically take the second number. If it's square rootable, no, that's a word. Then that's a difference of squares. I just want to talk through this last one here because that one's one of the hardest ones, the complex trinomials. So before I go any further here, do you guys recall how to factor this guy? Yeah, you're still looking for numbers that do add and multiply. It's just they're slightly different. It's still adding to give 7, but we're looking for numbers that times to give 6. That's because it's this 3 times this 2 right here. Normally, if there's not a 3 right here and there's a 1 right here, we can kind of ignore that. But now if there being a 3 there, we need 7 and 6. So 6 and 1. Now, it's not x plus 6, x plus 1, though. This one requires a little more work. You have to, like, split this equation up. Like, the 7 needs to get cut into pieces. You kind of cut it in half. Does this ring a bell? Okay. And then you do common factor. So what's in common between 3x squared plus 6x? We just did that right there. So 3x leaves x plus 2. And then over here, there's actually nothing really in common. So there's just a 1 in common, yeah. Factor out a 1, and you're left with x plus 2. And you need to get the same thing here twice. X plus 2 is one of them, and the 3x plus 1 is the other, yeah. It doesn't matter which order, though. So then one last thing before I move on here. This guy means x is -2, and this guy means x is -1/3. You guys recall this goes from last year? Okay, you may still need them along the way. So I think from here on out, we're just going to do a whole bunch of examples then, trying to practice our factoring of no longer to the power of 2's, quadratics, but we're going to try to go to the power of 3's, or 4's, or 5's, so that we can factor these guys. And again, like I said, this is kind of the culmination then of the last few days, trying to work up to this point. So let's give this one a shot. What we need to do here is we need to try to figure out what sort of things might logically be factors of this. So I'm going to give you guys some hints to start off with. I don't think x plus 22 is something worth checking. That makes sense? I would stick with low numbers like 1s and 2s and 3s and 4s. That makes sense? Like, don't go crazy. Like, don't make it too high. But there's one more number that we can work with here. And it's this very last number. It can actually help you give some advice as to how to make this work. For example, there's no way that this could somehow be like, say, x plus 2 and x plus 3 and x plus 3. And I can tell you why that won't work. This 2 times by this 3 and times by this 3, when those eventually get FOILed out, that is going to be what makes the last number. Does that make sense? Like when you FOIL this guy into this guy and then FOIL that into the last guy, this last number is the product of whatever this times this is. So, I mean, 2 times 3 would give you 6, but if you times by another 3, it would give you 18, and that really wouldn't work. Does that make sense? So as a way of trying to narrow down which numbers to use, I'm going to recommend let's work with numbers that could somehow possibly make the number 6 by multiplying. So like it could be 1 times 2 times 3. That makes sense? It could be -1. Actually, it has to be -6 technically. So it has to be like, say, -1, +2, and +3. It could be -2, -3, -1. Does that make sense? So before I actually try to do any synthetic division, I want to try the remainder theorem. So here's how the remainder theorem works. Pick a number and plug it literally into the equation and see whether it equals 0. So give me a number. Perfect. Let's start with 2. If we did f bracket 2, that means you're doing 2 to the 3 plus 2 times 2 squared minus 5 times 2 minus 6. All we're looking for here is, does this equal 0 or not? Yes? Perfect. Okay. Again, to some degree, you're kind of just throwing mud at the wall and hoping it works. If 2 did not work, we'd just pick another number. Does that make sense? But we found one that works. So here's what I'd suggest we do next. Now let's try our synthetic division. So if 2 is the root, what is the factor? Perfect. So go x minus 2 and synthetically divide it into a 1, a 2, a minus 5, and a minus 6. The remainder theorem on its own is not enough because we need to know what the leftovers are. I'll show you what I mean by that in a second. So, how do you synthetically divide? Drop down the 1, bounce. Minus 2 times 1, minus 2. Subtract. Minus 2 minus minus 2 should be 4. Bounce again. Minus 2 times 4, minus 8. Subtract should be 3. Minus 2 times 3 is minus 6. When you subtract, you better get 0, right? Because otherwise you screwed up something. Why did I just go through this whole process of long dividing? No, it's because I need this. I did all of that for this.
So now you know what
Now I know what the rest of it is. So here's how I can write it. It is x minus 2 times by x squared plus 4x plus 3. See how I've broken a factor out of this? In a way, here's what I've done. This f of x right here is really the byproduct of like a g of x times by an h of x. I've managed to turn f of x and like break it slightly apart. Have I broken it all the way apart yet? No. What I really need to do now is figure out how to break this h of x apart into 2 more of them. However, hopefully by now you're able to kind of look at this thing and say, hang on, I know how to factor this. What numbers add to your 4 and times to your 3? Ta-da! So then this guy can become x plus 3 and x plus 1, and then I still have my x minus 2. This is what my f of x now equals. And I found a way to pull it apart, and I factored it into 3 pieces.
Is there any way to equal that make it equal to 0?
Yes, like sometimes things are not factorable. So you know how like, yeah, For right now, I'm going to try to give you things that should be solvable, but there is the possibility, you know how like last year there was there is no answer? That is still possible sometimes. So for the most part though, I'm going to give you questions that can be factored. Otherwise, I don't know what we're doing it for. Does that make sense?
Yeah.
So, one quick way to check here. You guys know how I told you that this 6 right here was kind of the key number? Look at the last digits we had here. A -2 times a 3 would give you a -6. Times that by a 1. So a -6 came from. Wait, one last thing. We're actually not done yet, though. We were asked to like find the roots and solve. So this guy means x is 2. This guy means x is -3. And this guy means x is -1. Sound good? Okay. That's how you factor cubics and quartics and quintics and so on. It's actually not all that nice. Like, it's not an easy 1 or 2 step thing. It actually requires the culmination of a lot of little skills. Like, if I were to walk back through all the skills we used, we had to use the remainder theorem up here and try to find a 0. So that's why we showed you that. You also had to use, like, long division or synthetic division. The only reason we had to do that, though, was to find this little bit right here so that we could times them together. I wanted to show you how functions combine. That's why I wanted to show you how like the f of x really equals g of x times h of x notation. I wanted to show you the idea that really we have small functions multiplying by each other. And then you still had to remember how to factor this, so that's a last year skill. And then you still had to remember that roots and factors are the opposites of each other. Does that make sense? I'm not holding out on you. There's not some sort of easier way than this, by the way. Sorry. Does that make sense? Okay, let's try another one. Actually, I guess before we do another example here, just a blurb. The integral 0 theorem basically states that if x minus a is a factor, then that number has to be a factor of the constant term. I already talked to you guys about this, I just didn't call it this theorem. Basically what this means is that when you're trying to guess what numbers to plug in here, they have to be numbers that could somehow make up 6. So don't guess 5, because nothing times 5 gives you 6. I mean, not a whole number, obviously. Does that make sense? So that's what this theorem basically says, is when you're trying to figure out what numbers to guess, use things that are factors of that constant term. So let's try this one. Again, I'll just walk you through it, I guess. Where should I start? Where did I start last time?
Which number do you think?
We got to figure out what sort of factor we think could somehow work and base it on this last number here, 3. So what sort of things could somehow times and give 3? Yeah, probably a combination of 1 and 1 and 3. Now, I mean, it could technically be -1 and 3. That would also work. It could be 1 and -1 and -3. So we should test 1. Let's see whether 1 works. So start off by going, let's go f of 1. 2 bracket 1 to the third minus 5 bracket 1 squared minus 4 bracket 1 plus 3. The only reason I'm doing this is to see whether it equals 0 or not. I'm hoping that it will. So to some degree, you still have to like have a little bit of blind luck. Did it work? No? Okay. So, darn. Not a big deal. We'll test another number. Let's try 3. Let's see if the 3 works. 2 times 3 cubed minus 5 times 3 squared minus 4 times 3 plus 3. There's only so many possibilities. One of them has to work if this is actually factorable. That one works? Okay, so here's what that means. It means 3 is a root. You do synthetic, but with what? Good, with x minus 3. So now we're going to do our synthetic division. It's going to hopefully prove again that our work here was right, but we're doing this only to find the leftovers. So let's go x minus 3 and synthetically divide it into a 2, a minus 5, a minus 4, and a 3. So we're only doing this to find the little leftover bit that's down here. So drop down the 2. Bounce the -3 by the 2 to give you a -6. And then you're subtracting. But yeah, like subtracting is going to be adding because it's a double negative, so I think you get 1 right here. -3 times 1, when I bounce back up the -3 here and subtract, you should get a -1. And then -3 times -1 should give you 3, which gives you 0. So again, this is a good way to double check because you still have a remainder of 0. But that's not why we did this. The reason why we did it is because we needed this leftover bit. The leftover bit is 2x squared plus x minus 1. Still with me? So what this means then is that our big function f of x can really be written now as like g of x times an h of x. My g of x being the x minus 3, and the h of x being the leftovers, the 2x squared plus 1x minus 1. Am I done? Let's see whether we can try to break the h of x thing apart into more. This is why I had that slide way back a few ago about how to do different sorts of factoring. This one's a little bit meaner though. This is where you have to like add to give 1. You have to multiply to give -2. Does that make sense? Why I'm doing like the 2 and the -1? What adds to give 1 and multiplies to give -2? Yeah, that should do it, right? 2 and -1. 2 and -1. You need a lot of room. So I don't just go to x plus 2, x minus 1 though. I have to actually like break this thing into pieces. So you got to go like say 2x squared plus 1x minus 1. And I've got to go like this. We're going to split this guy into like say plus 2x minus 1x minus 1. Cut it in half. Find what's in common. So on this left-hand side here, there's a 2 and an x for both of them. Should leave you with x plus 1. And then for the other guy here, minus 1. And it should leave you with x plus 1. Okay, I think we're finally done now. F of x can be broken up into 3 different pieces. One of the pieces we found actually a while ago now, and we knew this piece from like this step way up here. I knew that x minus 3 was going to work from this step here. Does that make sense? Really, most of our work was for finding the other pieces. So then the other pieces are x plus 1 and 2x minus 1. So my goal was actually to, I think, solve it. No, I just said factor. So I guess we're done. If I had asked you to solve it and it was equal to 0, though, you'd have an answer of 3. You'd have an answer of minus 1. And you'd have an answer of a half. All right. Does that make sense? Something you can follow? The hardest part now is probably, can you do it on your own? Okay, let me give you a couple tips of advice. When we start off here, I'm going to only do written response to begin. But when we eventually start doing some diploma prep, one of the nice things about the diploma is that it's multiple choice, which means that really there is no show your work. So there is a trick you can sometimes play if it's multiple choice. If, like, say, answer A was what I just wrote here, and answer B was, say, x plus 3, x minus 2, x plus 6. What you could do sometimes is like look at the 4 answers and see which ones are reasonable. Sorry, give me 1 second. See how here the minus 3 times by the 1 times by the minus 1 must give you that 3 that was sitting up here? I might be able to narrow down a wrong answer by looking at it saying 3 times -2 times 6 That's not going to work because that won't equal 3. Does that make sense? So sometimes you can kind of narrow down the wrong answers when it's multiple choice. Okay, go grab cheese sticks.
There's cheese and fruit.
Oh, there is fruit. I didn't see the fruit.
Yeah.
Fire away.
Okay, so do we need to know how much long division work?
You don't need to do long division. Synthetic probably is faster. I wouldn't say this. I have seen test questions before, though, where they show you somebody else's work doing long division, and they ask you where is the mistake.
Okay.
So you probably don't have to do long division yourself, but you should be able to recognize how it works.
Okay.
Does that make sense?
Yeah, I know I want to know. Just because I'm kind of understanding this. I don't
You were
like,
here yesterday, so.
I'm here.
Right.
But yeah.
I can talk you through long division, but as a general rule of thumb, you don't ever really have to do it long division lesson.
And so for synthetic vision,
Yeah.
and so you times it and then you subtract it and you times it again and subtract it. Okay. Sure, I understand.
Okay. You guys want to try one on your own? Not this one, though. You guys want to do one more together?
Yeah.
Okay. You still got time. I still got about half an hour, so. Okay, what makes this one more challenging then? It's now the power of 4. Yay. Same skills. We don't need new skills. We just need to apply them to a more challenging scenario. That's all. Where did we start last time? Yeah, find numbers that can go into 24. Let's start at the bottom. Let's start with 1. 1 to the 4 minus 5, 1 to the 3 plus 2, 1 squared plus 20, 1 minus 24. Thank you.
Yeah.
Just make sure you close the door. Thanks. Yay. Darn. Okay. Next number up. 2. Do you guys know how to go, like, if you have an older style calculator, or even one of the newer ones, so you can, like, go up to the previous line and just, like, literally change out all the previous numbers? Do you guys know how to do that? Let me just show you in case you don't. So, like, here's what I might do. If I just tried doing 1 to the 4 minus 5, 1 to the 3 plus 2, 1 squared plus 20, 1 minus 24. And that didn't work. Here's a trick. If you don't have a calculator that like literally lets you go back up, because I know some of them do, go second, enter, and what it's going to do, it's going to pull up the previous line of work. And then if you go back, I can then type in 2, 2, 2, and 2. See how that might be a little bit faster? And you can keep doing that. If 2 didn't work, we could try it with 3, or we could try it with -2. So, does that make sense? So f of 2 apparently works. Lauren, could you close the back door? Sorry, I hate noise in the hallways.
We only need 1, right?
We only need 1. Okay, so we found a number that works. By the way, there is one way that you can just try to guess and check every possible number. If you can find 4 of them that work, those are probably your 4. That being said, there's one problem with that method. What happens if a number is used twice? Like, what happens if when you FOIL this out, it's x plus 1 again, and then x plus 2 and x plus 3? So randomly guessing and checking just all those numbers I find is not as effective. So let's try to break a piece off of this function then. I know one of the factors is x minus 2. That makes sense? Thank you. So synthetically divide it. 1 minus 5, 2, 20, minus 24. I'm just going to go through this now. Is that okay? You guys have the concept. I won't walk you through it anymore. It's 2, it's minus 3, it's 6, minus 4, it's 8, it's 12, it's minus 24, that's 0. You guys okay if I just do that?
I can still do this wrong.
Okay. I can sit with you later if you want. So in terms of this, it was pull down the 1. Minus 2 times 1 gave that minus 2 there. We then subtract to give the minus 3. The minus 2 and the minus 3 gave me the 6 here. Subtract for minus 4. 20 minus 8 gives me the 12. And then minus 2 times 12 gives me the 24, which gave us 0. So here's what we've accomplished so far. We've managed to break up f of x into x minus 2. And then working backwards, that's an x squared, and that's an x to the third. Yeah. Yeah. That's what sucks. We have to do it again. We now have to do the exact same process on like this bit right here. We should probably find a different one. Here's the thing. X minus 2 could be in this guy as well. But you know how like way back up here when we were testing numbers, did someone tell me that f of 3 worked?
Yeah.
Well, let's use 3 then. Does that make sense? Because I know 3 should then work as well. So now I'm going to take just this bit right here and do the x minus 3 then. So we need a 1, I need a minus 3, I need a minus 4, and I need a 12. Because I'm taking this guy and trying to split it apart now. So more synthetic. Drop down the 1, times them, that gives minus 3. Okay, this is okay. That's going to subtract to give a 0, which will make that a 0, which will make that a minus 4, which will make that a 12, which will make that a 0. What does this mean then? Working backwards. So that's your remainder. That's your constant term. It means you have no x's and you have x squareds. So breaking this up into pieces, what does my f of x equal then? I had an x minus 2. Yeah, that's gross. I had an x minus 2 because of this guy right here. I had an x minus 3 because of this guy right here. And then what's the leftover bit? X squared minus 4. Fantastic. It's a difference of squares. So you know how, Drianda, a second ago you asked whether we could use 2 again? We probably could have. But I had no guarantee that 2 was going to be in this thing twice. It looks like it's an x minus 2, an x minus 3, another x minus 2, and an x plus 2. Those are my 4. If you were to just randomly guess and check numbers by plugging in, like 2 into your equation and 3 into your equation, the biggest reason why I suggest you don't do that is what happens if one of the numbers is used twice. You'd never find it. Does that make sense? So it looks like 2 should work. It looks like 3 should work. It looks like 2 should work again, so that doesn't have anything new. And it looks like minus 2 should have worked. Those are our x-intercepts or roots or whatever you want to call them. What did the question ask for? Okay, it just said factor. So I guess we were done right here. If it had asked for x-intercepts, that's what this would have been. Yeah.
How did you figure out that x minus 2 is something that thing?
Oh, you would have had to. So you'd have had to go back up. Like, you know how up here we were just guessing and checking random numbers? I just picked the 3 because I think Haley told me that 3 worked.
Oh,
so that makes sense.
The original thing?
It should work for the original, although you could actually plug it into this one right here as well. Because if it works in the original, it should work in the slightly smaller one. So you should be able to plug it into either one.
So you would do that and then say you would actually find it, you try to find the x minus 3 to the second
You could do it through the second equation, or through the first. You should be able to do it through either. Okay. So like I said a little while ago, I'm not holding out on a shortcut. This is the method in which we try to factor large polynomials. Like I said, it's the product of a lot of little skills. So hopefully you can kind of see why I taught things in the order I did. It's because we need to do a lot of little tasks to try to figure this out. So, okay, you guys brave? Try this one by yourselves. Is this our last one, by the way? Or is there more after this? I don't know. But is there not? Okay, how about this? Let me just talk through the slides here, and then we'll finish with this one here. I just want to point out, when you're talking about cubics, then, cubics, you could have one answer. See how there's just that one guy right there? It is possible for there to be one answer. It is actually possible for there to be two answers, like for roots. And there is the possibility of 3 answers. Is there the possibility of 0 answers, though? On a cubic? I would say no. It like a cubic, no matter how I draw it, has to cross that line somewhere. Okay? Similar principles kind of apply with degree 4s and 5s and 6s. It is actually possible for a degree 4 graph to actually not have any answers. Or it's possible for it to have 4 of them. Or it's possible for it only to have 2 somehow. So I just want to point out there's a whole bunch of different possibilities as to how well something actually can be broken down. So, okay, that being said, why don't you guys give this a try then? See whether you can do it yourself. So focus on the number 3. So if that last coefficient is 3, you really only have 4 possibilities that are worth checking, right? I've only actually had you guys check positive numbers. So you should probably check positive 1 and positive 3. But if positive 1 and positive 3 don't work, don't forget to try checking a negative 1 and a negative 3. Does 1 work?
Yeah.
Oh, good. I always like it when 1 works because it's like the first one I try. Right, because that's 1 minus 2 is minus 1 plus 4. Yeah, 1 works. Is anybody trying it with a number other than 1?
I did all 4, none of them worked.
Oh, you didn't get 1 to work?
No.
Try
1 works.
Try 1 more time then.
1 more.
Because apparently 1 seems to work. So yeah, drop the 1 down there, and then times this one by that one, so negative 1, and that bounces up into this one. Then subtract these 2. So minus 2 minus minus 1. So it's minus 2 plus 1.
Sorry. Yeah, okay.
Does that work?
Yeah, but we can't get.
So then now bounce again. Minus 1 times minus 1 should give 1. And then 4 minus 1 will give 3. Minus 1 times 3. Bounce again, negative 3. When you subtract those, you get 0. Alright. Yes? What was that?
That's the part where we get,
Were you trying to factor?
and then we can't find numbers yet.
Okay, so for some of you guys who get this far, there was a point I'm trying to make behind this question. I just want to go back to the slide here. If you can't factor, yeah. So if some of you guys get to the point where you've managed to do your synthetic division and you get to that section where you found your leftovers and you can't factor, don't forget you can try the quadratic formula. Like I said, this really is the culmination of a whole bunch of previous skills you've learned. So let me put some work up on the board just to follow you guys. So I'm thinking most of you probably did x minus 1 like this, right? 1 minus 2, 4 minus 3. Plus 1, 3, 0. Okay, so did you guys get to this point here where you get x minus 1 next to x squared minus x plus 3? Okay. There is the possibility that this leftover bit here is not something that you can factor. So you can still try the quadratic formula. Yay. You guys remember the quadratic formula by memory? 4ac. Yeah. Okay. So if you guys have gotten a little ahead of me here, it looks like you get a negative under the square root sign. Yeah, just put a number there. So that just means that there is only, you know how there was the answer, there is no answer? That means that this stuff right here contributes no roots. However, does this graph still have a root? Yeah, it still has the root of 1. So by the time we're done this thing, x is 1. Because this guy right here is, this kind of sucks. We did all of this work right here, and it did nothing for us. Because there was no answers given. Does that make sense? That's kind of one of the reasons why I think I had this slide afterwards to show you. It is possible on a cubic that this part of the cubic right here could provide an answer, but like the quadratic part of the cubic right here, see how the quadratic doesn't get low enough to actually go across the line? This part right here is like a no answer section, but this guy right here is where that x was equal to 1. So that is a possibility. You guys able to do most of that minus the quadratic by yourself though? Awesome. Okay. So a quick summary then. We've got the halfway point of our units. Not that all of the first skills that we learned aren't important, but I said this a lot today. Hopefully you'd agree. I've been teaching you a lot of these first couple of days with today in mind. The idea of the factor theorem and the remainder theorem, they kind of go together. Even the idea of how functions can be multiplied by each other. The day where we put like a function inside another function, that doesn't really apply to today, I guess. But pretty much everything else, the idea of, putting multiple functions together, that's really what we just did. Right here, we took a very large function and we figured out that it is actually the product of like this function here times by a different function here. The idea of you can actually multiply them together. Questions, comments, concerns, conundrums, curiosities, complaints? You guys good? It does, yeah, it sucks. Like, don't get me wrong, it's not enjoyable, and there's not a better method. Okay, you guys have like 10 minutes left today. Can you guys make sure, to the best of your ability, that I get the assignments before the end of the school day? I will take them late, and I'll still mark them. The only thing is then I'm going to make you count a late assignment on the progress log, so you can't omit it. Does that work? Okay, cool. You guys have 10 minutes, I guess, to do stuff. I'll be right there, Gianna.